In this work, we are given a single image of a human, without any information about body pose, scene, or camera calibration, and we wish to obtain both 3D shape and pose from the picture. This is a long-standing problem with many applications. So far, most methods in the literature focus on just obtaining the 3D pose as a skeleton, without the body shape. But the human body is not just a skeleton, it has volume. Here, the skeletons might look reasonable, but when we fit a body to it, then it's clear that it has unnatural body proportions, or that the shoulders and hips are too narrow. These errors are not obvious from just looking at the skeleton, so it's important to solve for the shape as well as the pose. There are a few methods that solve for both pose and shape, but require manual intervention, or multi-view or video sequence. Our approach is fully automatic, and operates just with single views. Furthermore, we demonstrate our approach on natural images with complex poses. Our output is realistic and can be immediately posed or animated in standard graphics pipelines. Our approach works on a variety of images, like this sequence from the Muybridge footage. We do this in two stages. First, we estimate the locations of 2D joints using a state-of-the-art CNNs. Then, we take a generative model of 3D human bodies, called SIMPLE, and directly optimize its parameters so that the model joints project to the detected 2D joints. This fits within a classical paradigm of bottom-up estimation, followed by top-down verification. We can obtain shape from just the joints, because SIMPLE captures so much information about human body shapes. We call our approach Simplify. In detail, for the CNN stage we use a recently published method called DeepCut, which outputs a set of 2D joints with confidence values. Note that you could replace this with any 2D joint detectors. For the 3D generative model of humans, we use SIMPLE, where the human body is parameterized by shape and pose. The shape is characterized by the coefficients of a PCA shape space, beta. The pose is represented by the relative rotation of the 23 joints in a kinematic tree, theta. To fit beta and theta parameters to the detected 2D joints, we minimize an objective function, which is the sum of the data term and 4 priors. The data term depends on body joints. In SIMPLE, the joints are regressed from the shape and pose parameters. Using these 3D joints from SIMPLE, we compute the joint projection error, which penalizes the differences between detected 2D joints and the projected SIMPLE joints. We solve for the camera parameters as well. Here, we show how SIMPLE changed during optimization from the template to the final shape. However, this problem is fundamentally ambiguous, because many 3D poses and shapes can explain the same 2D image. For example, given this image of a man standing, this model looks like a reasonable explanation, but if we see it from another side, we see that the knees are bent even though they shouldn't be. To overcome this, we need a good prior. So, we learn a multimodal pose prior from nearly 1 million poses in the CMU mocap dataset. We also encode a prior on joint angle limits. For the shape prior, we use SIMPLE's PCA space, which is obtained from thousands of scans. This captures the statistics of human body shapes very well, and is much richer than a prior on 3D skeletons. Another advantage of working with complete surfaces instead of skeletons is that we can reason about interpenetration. We do so by approximating the surface with capsules and penalize intersections between them. Here is a result without the interpenetration term, where there is a gross intersection of the left arm and the body. Adding the interpenetration term resolves this problem and makes the results qualitatively natural. Our final objective function is composed of the sum of all the energy terms. We demonstrate our approach on the lead sport poses, a highly unconstrained dataset with a wide variety of complex poses, clothing, background, and imaging conditions. To our knowledge, no other previous approaches have demonstrated 3D mesh reconstruction on LSP images. We also compare our approach to 3 methods on the task of fully automatic 3D joint estimation. All methods use the same detected 2D joints as input. We also quantitatively evaluated our approach on 2 widely adopted datasets, Human EVA and Human 36M, and achieved state-of-the-art results. Our approach is conceptually simple and easy to customize, so there are many avenues for future work. Results can benefit from cues like silhouettes, multiple views, and temporal information in video. Having an explicit 3D mesh may help occlusion reasoning in image understanding, and these meshes may serve as a training data for various applications. Our code and results are available online. Thank you.